This video is on section 7.3. We're going to look at theorem 7.6. It's a geometric mean theorem for the altitude to the hypotenuse of a right triangle. Here's how this goes. This red segment is the geometric mean of these two other segments, the blue and the green. That's the simplest way to put it. The red is the geometric mean of the blue and the green. Now, think about what these parts are. This red is the altitude to the hypotenuse. This blue is part of the hypotenuse, and this green is part of the hypotenuse. So that's what the math language says. The altitude from the right angle to the hypotenuse divides the hypotenuse into two segments, the green and the blue. The length of that altitude is the geometric mean of the lengths of those two segments. The red is the geometric mean of the green and the blue. Let's try some. Here's a right triangle. The red is the geometric mean of the green and the blue. So we're going to write a proportion. The red is the geometric mean. That's my unknown. It's the geometric mean of the two pieces of the hypotenuse, the 9 and the 3. So you cross multiply here and you get x squared equals 27. So x is the square root of 27. That needs simplified, remember. I know that 9 goes into 27. And 9 is a perfect square. It goes in 3 times. So to simplify this radically, square root of 9 is 3, and the square root of 3 does not simplify. The altitude to the hypotenuse of this right triangle, notice how I only knew the two pieces of the hypotenuse. It's 3 square roots of 3. That's where that theorem comes in to help you. Now, if you didn't have this geometric mean theorem, you could still separate your right triangles into 3, since they're all similar, and you could write a proportion. But knowing this is a little more efficient. Here's number 2. There's no colors on here. I could put colors on if I needed to. In fact, let's do that. The red is the geometric mean of the green, be careful there, and the blue. I know the blue. I want the red. The green is not listed here, but we can calculate it. That's why you have to be careful on this one. This one's a little bit different. See, on this one, they told you the two pieces. Over here, they don't tell you the two pieces. They tell you the whole thing in one piece. This green piece right here is 23. That's 23 plus 7. Okay, so the red is the geometric mean of the green and the blue. The red is the geometric mean of the green and the blue, 23 and 7. Cross multiply. X squared equals 23 times 7. I'm just getting my calculator out for this one because it seems like this one's going to be a little bit tougher. 23 times 7 gives you 161. And I got to be honest with you, I don't know what perfect square goes into 161. So I'm going to start trying some. I have my perfect square list in front of me. That always helps. So 161 is not on the list. I know that 144 doesn't go into it, and neither does 121, neither does 100. 81 almost does. I don't think 64 does. 161 divided by 49. That doesn't work. 161 divided by 36. That doesn't work. 161 divided by 25 isn't going to work. Try 16. No luck. 161 divided by 9. That doesn't work. 161 divided by 4 isn't going to work either. This is really, really odd. But that is your geometric mean. It is simplified, square root of 161. There's no perfect squares that go into that evenly. Let's try this next one. Again, there's no colors. The red is the geometric mean of the green and the blue. Now we have a number there, so that changes some things. The geometric mean in this particular problem is 10. So 10 is a geometric mean of 15 and a number. 15x equals 100. So x is going to equal 100 divided by 15, which gives me exactly 6 2/3. In my calculator, it says 6.666666 forever. I know that's 6 2/3. That's how using geometric means makes things a little bit quicker.